Alright class, we're now in the one categorical variable part 3 notes. We're going to talk about something called confidence intervals here. And although maybe you've never heard the term of a confidence interval before, you've probably actually seen a confidence interval. If you've ever seen like a survey results reported as 60% plus or minus 2%, so you might have seen something that looked like this. That is actually a confidence interval. And so that's what we're going to cover, is how these are actually calculated, how do they come up with that plus or minus part, and sort of the motivation behind it here as well. So we're going to start by talking through an example. So we had a random sample that was collected of 600 Boone County Elementary School students, and of those, 29% of our sample was eligible for free or reduced lunch. Okay, so let's start about what we already know. So we know that we're sampling 600 students. We know that 29% of our sample, so there, since it's coming from just the sample, that means that's a sample proportion, or it's our p hat, is 29%. Okay, so now that we have those two numbers, does that mean that 29% of all Boone County Elementary School students are eligible for free or reduced lunch? Or in a sense, what I'm asking here is, does that mean that P is equal to 29%? Well, first keep in mind P and P hat are two different things, right? So P hat is from the sample, P is from the population. So do we expect our sample to be perfect for our population? Okay, no. It's just a sample. It could be 29%, but we don't know that it is. But something we hope P hat is close to P, or that it's somewhere near. So we don't maybe think it's exactly 29% for P, but we think that hopefully it's close because we got 29% from our sample. So we expect that that's going to be close to what it should be. How close? That's what we're going to talk about for how we construct a confidence interval here as well. So how can we go about doing that? So in our one categorical variable part 1 notes, we learned that under certain conditions, that p hat, our sample proportion, was approximately distributed normal with a mean of p and a standard deviation of the square root of p times 1 minus p over n. So we had that. And once we knew that was met, we could use our normal curve rule. So if I wanted to find about 95%, so let's first do this visually, then I'll do it mathematically. So once we know our conditions are met, we have our sampling distribution, we know it's centered at p. If I want to get 95%, I'm going to go 2 standard deviations to the left and 2 standard deviations to the right. So that's how we're going to get 95%. Right, what's our standard deviation? So our standard deviation is the square root of p times 1 minus p over n. So mathematically, I'm going to label these two spots as A and B real quick. So how we would find A is we would take P minus 2 of our standard deviations. So I would subtract square root of P times 1 minus P over N 2 times to get that point. And to find point B there, I'm doing the same thing, except for I'm adding 2 standard deviations. So 95% of the time, p hat would be expected to be between those two numbers. All right, now let's talk about the problem with this picture. And the first one is the big one. We don't actually know what p is. Right, so if I ask us for our first example up here, okay, we have p hat, put it on your picture down here. Where does it belong? Is it bigger or smaller than P? We don't know. We don't know where to actually place that on our picture because we don't know where P is, so we don't know where the graph is actually centered at. Again, we expect P hat to probably be somewhere within this A to B area, at least 95% of the time it should be. So we know it should be somewhat close to P, but exactly where it falls on that picture, we don't know. The second issue is because we don't know P, we also don't know that standard deviation, since that actually has P in it. Alright, but think about, okay, if I knew where P hat was, well, maybe I could go out some standard deviations on either side of it. So maybe I could kind of change around what I'm working with. Before I knew P and I was trying to find P where P hat might fall, well, maybe if I find P hat, I can figure out where P is going to fall. So that's the idea of what this general picture before we do the formula is going to look like. So let's see how this goes. So from our general picture, I know it's going to be centered at P. Again, don't know exactly what that number may be, but I can still put P in the center. And for a general standpoint, I'm going to call this 1 minus alpha. So in our previous example, I put 95% in the middle, but I could put any percent I want in the middle. I mean, for example, we could have put 68, 95, or 99.7, but I can actually put any number. I can put 96% in the middle if I want. What that's going to mean for me, and we'll do it for this picture first. So if there's 95% in the middle, there's 5% left over. So half of it's going to go over here, half of it's going to go over there. So I would know that this would be 2.5%, and that this would also be 2.5%. Then I get my total of 100%. How this applies to my general picture. So if I have 1 minus alpha in the middle, I have alpha left over. Half of it's going to go over here, and half of it's going to go over here. And this is my distribution of P hat. All right, so P hat's going to be some number along the bottom here. Well, P hat's going to fall somewhere around this bottom part. But what I know is if it falls somewhere between here and here, and I go out 2 standard deviations in both directions, can't quite go all the way over that way, it's going to contain P. So it'll actually have P inside of it somewhere. So now I'm going to write that in words. So if P hat falls inside that 1 minus alpha area, when I construct my interval, it will contain P. If it falls outside of that interval, it won't. So what is this 1 minus alpha even telling us? Well, that 1 minus alpha is a percentage we're going to put in the middle, right? So we had 95% that we had in the middle. So we would say that 95% of the time, our p hat will give us an interval that will contain p. 5% of the time, it won't. So maybe you can see we have this sort of likelihood that our interval will actually have the right number in it somewhere. So that's why we might want to change that percentage that goes in the middle. Now that's a lot to have digested, but it's the idea here that hopefully makes sense. Because the math on this one, I will say generally the math behind confidence intervals is generally much easier for students than it is for hypothesis testing. But it's the understanding of what's going on for confidence intervals that can be a little bit tougher. So we're going to talk about first what the formula looks like. So you see the formula right here in this box. And all of these are symbols we've seen before. So p hat's your sample proportion. Alpha, I've kind of specified up here. So we can use the alpha as a percent that's not in the middle. So if you have an alpha of 5%, there's 95% in the middle. Z, so it's been a little while since maybe we've seen Z in this way, but Z measures how many standard deviations away you are. This is actually when we're going to work backwards in the table, so we'll get to practice that again here in a couple of moments. And then of course N is just your sample size. So no symbols in this formula are new to us. But there are a couple ideas going on inside this formula that are new. We have two new terms that show up when we start talking about a confidence interval. The first one is what's called a standard error. And for most students, you can think of a standard error as just being your standard deviation. It just means that it's an estimated standard deviation. So why would they call this an estimated standard deviation instead of just the standard deviation? Well, if you look more closely at what's going on here in our formula, so I'll try to circle it here real quick. This is our standard error. That's square root of p hat times 1 minus p hat over n. So why it's given a different term is before we had p show up in here, and now we have p hat. So it uses a different term to signify that it's an estimated standard deviation, not necessarily the actual one there. The other term we see here is the margin of error. This is how far off we believe we are. So in this formula, I kind of point out what that would actually be. So first of all, notice the only difference in this side of the formula versus this side is that over here we have a minus and there we have a plus. So the same structure applies to either side. So this is the standard error, this is also the standard error. So it's the same thing that shows up there. When we're looking at the margin of error, it includes the Z. So when you look at the general form for a confidence interval, it's some estimate. So in our example, that's our p hat, plus or minus, because that was the only difference on either side, a margin of error. Our margin of error was z times the square root of p hat times 1 minus p hat over n. Or down here, the estimate is still p hat. Your critical point is a z, and here we technically had a standard error of that square root of p hat times 1 minus p hat over n. This is just the general form of what a confidence interval will look like. So when you go back and look at this formula, once we've collected our sample, we're going to know most of these numbers. We're going to have our sample size. We're going to have our sample proportion. What we need to be able to do is find z. So we're going to practice this idea. So what that z is based upon is just how confident you want to be. Or in a sense, going back to that general picture here, what percent that you want to put in the middle. So if I want to be 90% confident, when I draw my picture, I'm going to put 90% in the middle. Now since we're trying to find a z, z's are centered at 0. Now if I have 90% in the middle, we have 10% left over. So we're going to split up here on either side. So if we have 10% split it into 2, we're going to have 5% on this side and 5% on that side. Our goal here is going to be find this number. That's going to be our z. So this is when we're working backwards with the table. So when we go to the table, we write down what we're looking for, and we want everything that's just to the left of that question mark. So we want the 0.9 plus the 0.05. So when I actually go to the table, I'm going to be looking for 0.9500. We bring up our table. You can tell from your picture your z is going to be positive. I'm going to go down my first column here until I find the 0.95 jump. So there's 0.9452 and 0.9554. I'm going to go over in those two rows till I find the closest thing I can. We find two that are equally close here, so you choose either one. I would not be upset. I'm going to choose the 0.9505. So I'm going to write that number down next. But again, that's not our actual z. The row and column that occurs at tells us what our z is. So our z is going to be 1.65. So if we're going to be 90% confident, z will be 1.65. Now we're going to do the same thing for 95% confident. We should already have a pretty good idea of what we should get for 95% confident from using just our normal curve rule. We're told that 95% falls within about 2 standard deviations of the mean. So we should expect to get something close to 2 for our z. So we have 95% in the middle, 5% left over, so we split up, so we have 2.5%, which in decimal form is 0.025 on either side. We're going to go to the table here looking for everything to the left of our question mark. So that's going to be 0.95 plus that 0.025. So we're going to go to the table looking for 0.9750. There's our jump. Closest thing we can find, we can actually find this one perfectly. So we find 0.975. Then using that to figure out what row and what column that occurs at, we get 1.96. This is a good time to try the third one of 98% confidence on your own. So pause the video here, have your z table, and see if you feel comfortable in finding the z. Alright, so the z-score you should have found would have been 2.33, 98% in the middle, 1% on either side. Go on the table looking for 0.99. Closest thing you should find is 0.9901, giving you 2.33. Now what you'll notice is the more confident we are, the more standard deviations we have to go out. So if I wanted to be 99% confident, I know I'm going to get a z that's bigger than 2.33. So I'm going to have to go out more standard deviations to be more confident. Generally, once you're at the z, the math is not bad at all. Before we dive in and do an example, I have steps for doing a confidence interval, just like we have steps to doing a hypothesis test, but slightly different looking steps. So just as with hypothesis testing, you're going to see many different confidence intervals, but the main structure of the steps will stay the same. The first we want to do is define our parameter in words. If you remember, a parameter is just a numerical summary of the population. For us here, that's going to be P. So what is P going to represent in words? Step 2, we need to get the conditions. So let me list the conditions over here for you. These conditions are going to look very similar to those that we've had in the last 2 sets of notes, with just small adjustments. We're still going to have a relatively random and unbiased sample. Before, we've had n times p was at least 10, n times p0 was at least 10. Now we're going to have n times p hat be at least 10. Why p hat? We don't know p, so we can't use p. Next best thing we got is p hat. And in the same manner, your third condition will have n times 1 minus p hat. That also will have to be at least 10. Your next step is to calculate your interval, which is generally where students want to start on this, so notice that at step 3. And last but not least, of course, is going to be an interpretation. Next thing we're going to do is an example. And so we're going to go back to our opening example where we had a sample of 600 Boone County Elementary School students. We found that 29% were eligible for free or reduced lunch from the 600, so that was just a p hat. We're going to construct a 90% confidence interval for p. Alright, so our first step, as it says above, is to define the parameter in words. So our first step, so P here is going to represent the population proportion of Boone County elementary students who are eligible for free or reduced lunch. All right, our next step is to do our conditions that we have above. So our relatively random and unbiased sample. It says they took a random sample, so it's just a simple random sample there. No stratifying, no system to it. From what's given to us, there's no known bias. Then we're going to take n times p hat. So we have our n is 600. Our p hat is 0.29. So it gives us 174, which is at least 10. And n times 1 minus p hat will give us 426, which is also at least 10. So what this means is from our sample of 600 Boone County Elementary School students, 174 were eligible for free or reduced lunch, 426 were not. Alright, next here for step 3. The first I'm actually going to do is find my z-score, because what I want to do here in step 3 is do my formula. But if I look at my formula, I already know p hat, I already know n, I just need to worry about finding my z. So that's what I'm going to do next. So I'm going to draw my little picture here for me to find z. How confident are we asked to be? Okay, so we're asked to be 90% confident. So however confident we are goes in the middle. 10% left over, so 5% on either side. Goal is to find that number. So we're going to go to the table looking for 0.9 plus 0.05. So we're looking for 0.9500. Look for our jump, work our way over. 0.9505, closest thing, so then we find a z of 1.65. Now what you notice, what did I use to find my z? The only thing I need to find my z was how confident we were. The sample size didn't affect it. P hat did not affect it. 90% last time we found it over here was also 1.65. So anytime you're going to be 90% confident, that will be your z-score. So your sample size has no effect. P hat has no effect. Now that I know my z, I can plug things into my formula now. So I'm going to take my p hat minus my z times my square root of p hat times 1 minus p hat over n. And then also p hat plus my z times the square root of p hat times 1 minus p hat over n. And then I just need to do the math here. So making sure you know your order of operations all right. The first thing I'm going to do is take the square root. So I'm going to show maybe a little bit more work here than you need to. I'm going to carry a few more decimals to make sure I don't lose too much to rounding here. So that standard error is 0.018525. Then I'm going to do my multiplication. And then finally my subtraction and my addition. So 0.2594 to 0.3206. So there's the math done. Again, to work some terminology in here. So this 0.018525, that's our standard error. The 0.0306 is that margin of error. Now my last step here is going to be to interpret. But before I do that, what I've generally found is that students are better at interpreting percentages instead of leaving them here as these decimals. So I'm going to multiply things by 100% so I can make it percentages instead. So that's going to be 25.94% to 32.06%. At this point, all the math is done. All right, our last step here is to interpret. So interpretation is going to start with how confident you are. So we are 90% confident that, and then what our interval is, so between 25.94% and 32.06% of. Alright, so now going back to step one, what did we calculate? What are we interested in? So percent of Boone County elementary school students. Are eligible for free or reduced lunch. And if you read that interpretation, hopefully it makes sense. We're 90% confident that between 25.94% and 32.06% of Boone County elementary school students are eligible for free or reduced lunch. Now, to tie this back into how maybe you would have seen a confidence interval before, so looking right here, how you might see that written is as 29%, because that's our 0.29, plus or minus 3.06%. So that's your margin of error. And if you do that math, 29% plus or minus 3.06%, you do the minus, you get our 25.94%, you do the plus, you get the 32.06%. Alright, now using this interval, let's answer a question. Do you think that we could say more than 25% of Boone County elementary school students are eligible for free or reduced lunch? Do you think that would be a reasonable statement for us to make? Why or why not? Well, going back to our interval here, what did we find? So we said between 25.94% and 32.06%. Is that more than 25%? Yes. I should feel comfortable in saying that because my entire confidence interval is greater than 25%. All right, now let's talk a little bit more about this interpretation. So I seemed a little maybe picky on my wording with this interpretation. So the correct way we interpreted it, so we are 90% confident that between about 25.95% and 32.05% of Boone County elementary school students are eligible for free or reduced lunch. Sorry, I have my numbers slightly off within rounding there, so don't be too worried about that. What people might want to say is the probability that between 25.95% and 32.05% of Boone County elementary school students are eligible for free or reduced lunch is 90%. So to understand that distinction, I'm going to go back to one of our first pictures that I had here. So when we were looking at this picture, keep in mind, so P is a fixed value. We don't know what it is, but it's some fixed number here in the middle. P hat can fall anywhere along the bottom, so P hat is what can change. P hat is really what the probability is based upon here. So what do I mean by that? So if I look at a graph of my confidence interval, so we got 25.95% to about 32.05%. Look down here, so if I say, well, if P really is 30%, okay, my interval contains P, I had a good interval. Well, if you went out and took a sample of 600 Boone County elementary school students, Would you find exactly 29% were eligible for free or reduced lunch, or could your number be different? Okay, your number could be different, which means then that this calculation, you're going to get a different interval when you're done too, right? So maybe you construct your interval, and your interval goes from there to there. Does yours contain 0.3? Yep, so yours is a good interval as well. And each person could do this, right? We could go out and collect another sample, get another confidence interval, get another sample, get another confidence interval, and keep doing this here until I get some intervals here. So I can create all these intervals based upon different samples. And what do we find? So if we look at where 0.3 is, if I can draw somewhat straight here. So 9 out of 10 of them contained P. So what is 9 out of 10? That's what 90%. So when I say 90%, it means about 90% of my intervals will have P somewhere inside of it. It doesn't say where, just somewhere inside of it. So that's the idea of what that confidence really means. A couple other notes about the idea of a confidence interval is if you're more confident, how does that affect things? So for our example, we were 90% confident. If instead we would have been 95% confident, how would it have changed what we did in this problem? The only thing it would change here is in step 3. So we'd have the 95% in the middle. So our z-score would change. More specifically from what we found here. If we're 95% confident, our z would turn out to be 1.96. So I'm going to go out more standard deviations. What's that going to do to my interval? It's going to make my interval wider. So the more confident I am, the wider my interval is going to be. The less confident I am, the narrower the interval is going to turn out to be. So why is width such an important thing for me to bring up here? So let's suppose you asked me to estimate the percent of females on NKU's campus. So that was your goal. And I could come back with one of two intervals. I could say between 10% and 80% of NKU people are female. Or I might come back and say between 49.2% and 53.6% are female. Which one of those intervals would be more useful to you? This one's more useful. Why? So the first thing to notice is that it is narrower. Why is narrower a good thing? It's more precise. Or in a sense, it's more informative. I have a much better idea of what percent of people on campus are female when I have that second interval. The first one I could probably told you without even going out and collecting any data. Right, so I mean, the narrower it is, we might actually not like the answer, but we at least have a much better idea of what the answer really is. So how can we make an interval narrower? Well, the first thing is we just set up here, we could lower the confidence. So instead of being like 95% confident, if you want to be 90% confident, that'll narrow your interval. Or the other thing we can do is take a larger sample. Where we see that affects things is here in our formula. So as our sample size gets bigger, since it's in the denominator there, that standard error is going to get smaller, which makes your margin of error smaller, and then will make your interval less wide. All right, so that's where we're going to end this video. In the video next time, you'll get to do more examples of confidence intervals, as well as we'll talk about sample size.